So sorry for the technical glitch that we had. Again, I'm resuming. So we were doing this question in the previous lecture. We were trying to construct a Green's function for this particular problem, that is d3y upon dx3 equals to 0, such that y is 0 equal to 0 and y1 equal to 0, and given that y dash 0 plus y dash 1 equal to 0, we wanted to construct a Green's function for the same. If you want to construct the Green's function for the same, we know that the Green's function would be some quadratic function, because if you integrate it thrice, you will get this kind of function. And given all these conditions that we're imposing, after all, given all these conditions that we are imposing right now, so you'll get that. I think I'll just write them up here itself. This will be d plus e plus f equal to 0. So your d plus e plus f equal to 0. So your your d plus e plus f equal to 0. This is your equation number 1. Then I think equation number 2 was c was 0. This is equation number, I think, what should I say, 0 itself. And then you have another equation you had because of your another boundary condition which suggested that d plus 2d plus e must be 0. So your d plus 2d plus e must be 0. This is your condition number 2nd. And then if you see the another condition, that is this derivative condition, what you'll get, I think a continuity condition. If you see the continuity condition, you get a minus d zeta square, then b minus e zeta minus f must be equal to 0. Even if you write c minus, f, like it is fine, but already we know that your c is 0, so I'm just listing them out. So there are many conditions that you'll see here. And the last condition that you can derive out is from this particular thing. So this will give you, I think, if you just write the derivative part, so derivative will be 2dx plus ex. Ex का derivative will come 1. I think dx square plus dx plus f के हिसाब से चले तो it will be like the derivative condition would give you. अच्छा, this is equal to minus log, so right. So overall you will get, I think, 2d minus 2a zeta here. If I'm not wrong, please correct me if I'm wrong. Then there will be an issue if I'm wrong. So it will give you 2 times d minus a zeta, and then you have e minus b in plus, and then you have equals to minus 1. Is that clear? I think.
Yes.
Okay. So what I can do is I have 2 equations, right? So I have this equation and I have this equation, and I have e here in common. So probably I can cancel e out, but then there is f also here. So what should I do? Is there some mistake that I'm doing? Just try to find all these values. From this, try to extract some values for b and d. I think that would give you some answer. Now, if you have this c equal to 0, this is one condition. That is, one condition is this. This is fine. But then you have the unknown variables are, how many unknown variables are left? You just find those unknown variables. So you have in totality a, b, d, e, and f. These are total number of unknown variables. So you have total number of unknown variables. How many total unknown variables are there? There are 5 unknown variables. There are 5 unknown variables you can see. And how many equations are there? Like how many equations can you see here? So there are 4 equations, and you have 5 unknown variables. So this will lead to at least an inadequacy. In order, there will be inadequacy to find one constant. Okay, so one of the constant you may not be able to find. So one of the constant may not be able to find, because in totality there are 5 unknown variables and there are 4 equations. So if you have 5 unknown variables and then there are 2 variables, so you cannot solve it explicitly. So one cannot solve it explicitly. right? Is that clear to you? And if I cannot, one cannot solve it. If I cannot solve it explicitly, what will happen? There will be some. There will be an issue in identifying the appropriate Green's function. Okay. So in short, I can write. I cannot find. One cannot find. One cannot find an appropriate Green's function. Is that clear to you? So what happens is there must be some conditions as to like regarding the existence of Green's function. So there must be some like you can say conditions for existence of Green's function. Is that clear to you? Because see, whatever we have done, we know that if I'm saying that my Green's function is this, then these A, B, C's were only the things that we were finding using our conditions. Now here you can see that here you have 5 unknown variables and you have 4 equations. So 5 unknown variables and 4 equations you cannot find. Is that clear to you? So there would be some dependency, like one variable would obviously depend on another. There would be, even if I solve them up, even if I execute all my brain and try to solve this up, I know that these are insufficient conditions, isn't it?
Yes, sir.
Am I audible, right? Nobody's.
Yes, sir. Yes, sir.
No, I'm audible. So nobody's saying that's why. Okay. Now, if I just write what all those conditions are, I'm going to write it now. So you can say that the theorem on, and I'm not going to derive it, theorem on existence of Green's function. Theorem on existence of Green's function. So let us consider a differential equation in general of nth order. So in general, let us consider a differential equation of nth order. So let us consider a linear differential equation of nth order. And that linear differential equation of nth order is given by Ly is equals to P naught x y raised power n, y raised power n, derivative of y with respect to n, derivative of y n times. And then you have this P1 x yn minus 1. And then you have this Pn x y. And this Ly, when executed, gives you some fx, where fx is some forcing function or driving function. So what we are doing is we're trying to drive these in very general way. So that is what I'm doing. I'm considering a differential equation, a linear differential equation of nth order, mostly your inhomogeneous case, where your P naught, P1, P, all these functions like P naught, P1, and all these functions are continuous functions of x. So continuous functions of x. And given the boundary conditions, and you have some boundary conditions, and let these boundary conditions in general be written as Bk. So Bk means your different Ks will give you different boundary conditions. So like this is given by some alpha K0. You just don't worry about all these things. These are just boundary conditions mentioned in brief. Okay, so in brief, all these conditions I'm writing like
Sir, what is this BKY?
this is BK. This is BK0, this is BK1, and then you have beta K2, this is y double dash 2 beta double dash, and all these things. I mean, these are all you can say that I'm just trying to write your boundary conditions. These are, if you just vary k from 1 to dash dash dash, and so you'll have these n set of conditions. I've generalized them and written them up. These alpha keys can be some real constants. I've generalized them up. So these are your boundary conditions, that given your boundary conditions and your differential equation, what all constitutes your what you can say, what all constitutes your Green's function. So if these are the conditions, then I will write here that here your you can say the conditions that B1, B2, B3 dash 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 Bn form n boundary conditions, n boundary conditions. Okay. Now, if I just write it as 1, I will explain you with an example. Otherwise, probably will not be able to get. If this is your equation number 1 and this is your equation number 2, if my equation number 1 and equation number 2, you can say, have only a trivial solution. So in mathematics, what do you mean by trivial solution? I'll let you know. So trivial is yx equal to 0. So if there is only this solution left, that yx has to be 0. If these two conditions are satisfied, and it has only one solution, that is yx equal to 0, then for operator L, for your operator L, which is given by general nth order linear different, this is L is your general nth order linear differential operator. Then for L, Green's function surely exists. Green's function exists, and it is unique. Let me just give an example and make you understand all those things. Okay, so it's quite difficult for you, I know, but overall, just try to assimilate what I've written. I've tried to just writing an nth order linear differential equation. If it is given by like Ly is equal to f of x, and given these boundary conditions, if these two equations are simultaneously satisfied, and it has only one solution, that is yx equal to 0, then for operator L, the Green's function exists and is unique. Let us come back to the problem that I was discussing. So let us do the problem that I was discussing. So let us understand it using the problem that I was doing. So let us see that my differential equation was d3y upon dx3 equal to 0, if I'm not wrong. And initial conditions were given as y1 0 and y0 equal to 0. And additional conditions were that y dash 0 should be equal to y dash 1 equal to 0. So this was it. Is that clear? So if I write first, what should I write? Your yx must be equal to what? Your yx must be equal to, in general, ax square plus bx plus c. That is 1. I'm not writing Green's function here. Anywhere you can see that I'm not writing Green's function here. I'm just saying that if the solution of this 1 and solution of 2, that is all these boundary conditions, if I am left with trivial solution, that is yx equal to 0, then only my Green's function exists and it is unique. So let us understand what will be the solution for this differential equation. It will be simply ax square plus bx plus c. I'm not writing Green's function, forget about it. Second, y0 equal to 0. What does it mean? It means your c must be equal to 0. Your y1 should be equal to 0. What does it mean? It means your a plus b is to be 0. I mean, y1 कहाँ गया? देखो ना, c already 0 हो चुका है. Now, if you see your y dash 0 must be equal to y dash 0 plus y dash 1 should be equal to 0. What does it mean? Y dash 0 would be what? Y dash 0 would be, I think, b, है ना? और y dash 1 क्या होगा? I guess it should be b plus twice a should be equal to 0. That implies your twice a plus twice b should be equal to 0. Is that clear? So how many conditions there? The c equal to 0 is one condition. Second condition is this. Third condition is this. Is that clear?
Yes, sir.
Is that clear? अभी समझ में आया कि नहीं आया?
Yes, sir.
हाँ भैया.
मेरी आवाज आ रही नहीं आ रही है? Is that audible?
Yes, sir. Clear.
हाँ भैया आ रही है आवाज.
Am I audible? Was I not audible for all this while?
We are audible.
Why your people voice is not coming to me here?
Yes.
Um, am I audible? Am I audible right now?
Yes, sir.
Okay, you people were not audible. Okay, so kindly understand what I was trying to say, that we've already had this particular differential equation above, and we were not able to find the values for A, B, C, D's, E's, and F's because you had 5 values and you had 4 equations, so you cannot solve it explicitly. So there should exist some conditions on existence of Green's function. That is what I was addressing. I have written this in general. So if in general you have this Ly is equal to f of x1, and secondly these boundary conditions 2. If I simultaneously solve these 1 and 2, and if I end up getting a trivial solution, that is yx equal to 0, only then for an operator L you have a Green function. So let us try to execute using the example that we were doing. So the example that we were doing was d3y upon dx3 equal to 0, y0 equal to 0, y1 equal to 0, y dash 0 equal to y dash 0 plus y dash 1 equal to 0. So what will happen? So you can see that this c has become 0. Now, in order to find a and b's, I have to solve equation number 2 and equation number 3. But you know that these are two parallel lines. So if I draw a plus b equal to 0, and if I draw 2a plus 2b, so they will never converge. So there will be infinite number of solutions. There will be infinite number of solutions. If you remember from your consistency of equations, that if you have two redundant equations, these are two redundant equations, isn't it? These two redundant equations would eventually give me infinite number of solutions. And what I told you, that if at all Green's function exists, then this Ly equal to fx, that is equation number 1, and these boundary conditions, that is equation number 2, in together should give you a trivial unique solution, that is yx equal to 0. If it gives you yx equal to 0, only then your Green function would exist and should be unique. Otherwise, no. Is that clear? So therefore, you can understand that this particular boundary value problem, hence for this boundary value problem, there does not exist a Green function. There does not exist a Green function. Is that clear? Is that clear?
सर इसमें हम a की वैल्यू डिटरमाइन नहीं कर पा रहे इसलिए ये ऐसा हुआ है.
Right. A plus B की value कैसे determine करोगे? You have two equations, and both of these equations are redundant. A plus B equal to 0 and 2A plus 2B equal to 0. So whenever you have solutions, what you do? You try to make the graph. So basically, if I make a graph of A, B, if it is given like this, so it will be a graph like A plus B equal to 0, and this is 2A plus 2B equal to 0. So these are two parallel lines. isn't it? So you cannot form a solution by parallel lines. Is that clear to you?
Yes, sir.
So these are two reductions. So there would be infinite number of solutions. You just take like a equal to minus b, and if you take a equal to minus b, then you have these infinite number of solutions. These two are redundant equations. Basically, you will never converge to a unique solution from this. So you can have infinite number of solutions. Since you have infinite number of solutions in a and b's, you have infinite number of y of x. And since you have infinite number of y of x, you are not ending up getting yx equal to 0. So only if this particular equation number 1 and equation number 2 yields you a unique trivial solution, only then your Green's function exists and is unique. I hope I have made my ground clear. I'll give you a few more examples so that you can understand what I'm trying to say. So let us take a few examples that we've already done. है ना, तो उससे समझ में आ जाएगा guys. What should I give you? चलो देखते हैं. So let me give you another example. Just give me a minute. Okay. Okay, so this is, I think you'll be able to do this. Just give me a minute. Okay. ठीक है. एक मिनट दो मुझे बस. So try to solve this. So find whether or not Green's function would exist for the same. So is there an appropriate Green function for this particular boundary value problem? So if you have this condition, so y double dash x equal to 0 means what? It implies that your yx must be equal to what? Your yx must be equal to mx plus c. Is that clear? This you've already done. And your y0 is equal to y1. That implies if y is equal to 0 is equal to 0, y is equal to 0 is equal to y of 1. That implies your c must be equal to m plus c. Is that clear? And y dash 0 must be equal to y dash 1. If I say what is y dash 0, my y dash 0 would be, I think, simply m. And what is y dash 1? So again, if I take y dash 1, this will be again equal to m. So it is m equal to m. So here you can have, so this is how it is. And here you can have m equal to 0. From here I know that if I place y0, it will be simply c. And if I write my y1, it will be simply m plus c. So here m equal to 0 comes out. And this particular c, how many solutions can exist? There can be infinitely many solutions, isn't it? So if you have infinite many c's, you have infinite many y of x. So there are infinite many solutions. If you have infinite many solutions for the boundary value, like for this particular differential equation, including these two boundary conditions, I know my Green's function cannot exist. Because for Green's function to exist, satisfying this and satisfying these boundary conditions, the solution should come as a trivial 0. That is, yx equal to 0 should come out. If that comes out, then Green's function exists and is unique. So here, the Green's function will not exist. Is that clear?
Yes.
Okay. So let us do another one so that at least you are able to figure out. All these things are not going to come in exam. Don't worry about it. But just I want to let you know that is why I'm doing it. Okay. So that you don't do mistake in your exam. Okay. So these are two conditions. Now, let us move ahead again for our inhomogeneous cases, because that are very important for our examination point of view also and physics point of view also. So, but before that, if you want to solve another problem, I'll give you that particular problem. So find me the Green's function. Find the Green's function for the following. So let us give an again take a break and take this example. So xy double dash plus y dash equal to 0, and your y0 is bounded, and your yl is equal to 0. Your yl is equal to 0, your y0 is bounded, and xy double dash plus y dash equal to 0. Why I'm giving it? Because this serves as an example for Cauchy-Euler equations. So if I have done yesterday, these are nothing but these are Cauchy-Euler equations. In Cauchy-Euler equation, what do? You try to construct a format where you have this thing. So let's just multiply this with this. And now I know by suitable transformation, that is x is equal to e to the power z, I can write it as d bar into d bar minus 1 plus d bar y equal to 0, where d bar is equal to d by dz. Is that clear? Now, if you just take this example, you will get d bar square y equal to 0, and which implies your y as a function of z, y as a function of z would be equals to what? It will be equal to c1. I think z plus c2, and in other words, I can write c2 ln x plus c1 ln x plus c2 in y as a function. Is that clear to you? Is that clear to you?
Yes.
And your y0 should be bounded. So if your y0 is bounded, what does it imply? It implies limit x tends to 0, ln x, we know that it goes towards minus infinity. Yesterday, I also talked about it, and again, I'm making the graph. This is your graph of ln x, and you can see that as x tends to 0, your ln x goes towards minus infinity. So it implies that your c1 must be equal to 0. And if your yl is equal to 0, it implies what? Now you are left with this c2 only, na? So yl equal to 0 means what? It implies c2 equal to 0. So your c1 equal to 0 and c2 equal to 0 implies what? It implies your yx should be equal to 0. What does it imply? It implies that when I was solving this particular differential equation 1, this is your equation number 1, and along with the boundary condition, the solution that turns out is yx equal to 0, it implies this is the trivial solution that comes up. And since a trivial solution comes up by solving your yx and these boundary condition, it implies your Green's function should exist and should exist uniquely. Is that clear? And now let us try to figure out what will be the Green function. Is that clear to you? I have used the existence of the the theorem on existence of the Green's function. Is that clear? Am I
Yes, sir.
audible or not audible? I don't. Okay, ये बात समझ में आ गई होगी. Now, if I just try to find what would be the Green function, so you know that Green's function would obviously satisfy the differential equation. So if it satisfies this differential equation, your gx comma zeta should come out as c1 ln x plus c2 and c3 ln x plus c4. Your x lies between zeta and I think 0. Sorry, and your x lies between zeta and L. Is that clear? So if I try to solve these, now the first boundary condition that suggests is that your G at 0 plus should be bounded, because at 0 exactly you do not have the definition for Ln x. So if it is bounded, that implies your C1 should be equal to 0. So your G x comma zeta should be such that your C1 is 0. So forget about it. Now I already know that my G zeta plus zeta should be equal to G zeta minus comma zeta. So your Green's function should be continuous at the bound at the place there where there's a change in the definition. Also that I know that my G L comma zeta must also be equal to 0. So if your G L comma zeta is 0, that implies what? It implies your C3 ln L should be equals to minus C4. So in short, I can write my function as C2. X lies between zeta and 0. Now 0 you can take inside, and this is zeta and this is like L, and here instead of C4 you can write minus C3L. So this is C3 ln x minus ln L. Is that clear? Now if you use the condition of a continuity, if you use the equations to the continuity, you will get your C2 equals to C3 ln zeta minus ln L. So what I can do, I can write my C3 as C2 divided by ln zeta by L. So in short, sorry, I can write my G x comma zeta is equals to what? Is equals to C2, and C2 I'll write as it is. This lies between x and zeta, and if x lies between zeta and L, this is C3. C3 is given by C2 divided by ln zeta upon L, and then you have ln x upon L. Is that clear? I mean, I'm doing something wrong, or like, is that clear, or have I done something wrong? Nobody's responding. I do.
सर C3 को डायरेक्ट नहीं लिख सकते क्या, C2 log zeta val?
हाँ वही लिखा बेटा, C3 को I have written C2 upon log zeta val, है ना? C3 I have written C2 divided by log zeta val. This is what I have written.
तो दूसरी log की टर्म कैसे आ रही है?
This ये वाला term
log x by l लिखा है आपने।
log x by l होगा बेटा, log x minus log l. देखो
ओके ओके
C2,
ओके ओके ओके, ठीक है
है ना? I hope it is clear. Now the derivative condition, that is gx at zeta plus and zeta minus gx at zeta minus comma zeta should give me minus 1 upon x. X at 1 is 1. Sorry, x at zeta. X at zeta is zeta. I think I should write zeta only here. So I'll write zeta here. Okay, so minus 1 upon zeta. You see the derivative of g. So here you have x. So the highest order derivative coefficient is x. So instead you just write minus 1 upon x, and minus 1 upon x is minus 1 zeta. Is that clear to you? I hope it is clear. Now if I just try to use these conditions up. So if I use these conditions, what I would get? To the left, I know the derivative would be 0 because there is only a constant. Here I would get C2, and these are all the constants. So I'll write it as it is. And this derivative will give me ln x upon L will come as simply 1 upon x upon L. That will be L upon x. Is that clear? This will be like this only, and then you will get 1 upon x at x equal to zeta, and this is equals to minus 1 upon zeta. I hope it is clear. So L gets cancelled here, and you are just having this minus 1 upon zeta. So minus 1 upon zeta plus 1 upon zeta is minus, like this is minus 1. So C2 you will get minus zeta. Is that clear?
Yes sir.
Okay. So overall, I have got the answer. C2 is coming out as minus zeta by L. Minus zeta by L. So I think, have I made some mistake or somewhere? Okay, so overall, you just see the sign. There may be a possibility that I may have done something wrong with sign, but overall, my gx comma zeta would come out as ln L by zeta. If I write from x lying between zeta and like 0, here it is a constant. And here if I write minus ln zeta by L, so this will come out as ln. You can write x by L. You can write a negative out. All x lying between zeta. I hope it is clear. अच्छा एक नेगेटिव यहाँ पर भी तो आएगा. अच्छा ये तो 0 हो जाएगा ना, टू द लेफ्ट एंड टू द राइट दिस विल गेट. हाँ ठीक है. सो यू विल गेट दिस. सो you are getting minus ln of zeta by L for all x lying between 0 and zeta, and for all x lying between zeta and L you are getting ln of x by L, and then negative outside. So overall this is your Green's function. So I told you that this particular Green's function would exist for this particular problem because when I was solving the differential equation and I was using these boundary conditions, the solution that I was getting for yx was a trivial one. So if I get a trivial solution, I know that my Green's function must exist and it should exist uniquely. And that is what I have shown in this particular problem, an easy problem, that this particular differential equation will have a Green function and uniquely, and this would be equal to this. Is that clear?
Yes.
Okay. Now you must be thinking that can we really find the solutions? Can we really find the solutions of differential equation, of inhomogeneous differential equation from Green's function? Answer to this problem is yes. Okay, so this is what we want to find. So this is what we want to find means this is our initial inquiry, that really can we really find the solution for the inhomogeneous differential equation using the Green's function. So here's a theorem that I'm going to write. So if, and then I'm going to continue with slightly a little bit of a lecture. I think hardly 15 minutes it would take, and there is another lecture for you. If gx comma zeta is your Green's function, for a Green's function is the Green's function you can say of the homogeneous case. Homogeneous case means inhomogeneous के अंदर you just take fx equal to 0. So that will form the homogeneous boundary value problem. That is L by x equal to 0 given these initial conditions, that is your b1 y is equals to b2 y is equals to dash 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 bn y equal to 0. ठीक है? Then the solution of the inhomogeneous problem that is what? That is given by Ly equals to f of x given these boundary conditions is nothing but this particular integral. Okay, so this is your y of x. So once you know the Green's function for homogeneous case, what you can do, if you want to find the solution of the inhomogeneous problem, that is, if I want to find what would be my y, so what I need to know that what will be the Green's function for the homogeneous case. If I know that g, then I can just integrate my gx comma zeta with your f zeta here, where f zeta is your this forcing term or your driving term. Your f zeta is your forcing function or your driving function, or you can say your in mathematics, so to say, your non-homogeneous part. Is that clear? So I'll illustrate all these things using a problem, and I'll meet you in the next lecture. Because right now there's a हाँ बेटा बोलो.
इसमें ये जो आपने सॉल्यूशन लिखा नॉन होमोजेनियस पार्ट के लिए, इसमें सिर्फ ग्रीन फंक्शन तो पता होना चाहिए ना?
ये Green's function पता होना चाहिए, and that Green function you should know for the homogeneous case. Like for example, if you replace your fx by 0, you just find a Green's function for that particular thing, and if you find a Green's function for that particular thing, then having known that g, you can integrate it with fx, f zeta in the interval of existence that is like that could be given to you from a to b, like wherever you are served on these boundary conditions. So wherever your boundary conditions are served in that limit, if you integrate it, you will get back your y of x. Because see, this integration is going over zeta. So eventually, all these a's and b's will be filled by zeta. I mean, this is an integration over zeta. So you will get function of x. Is that clear? So I'll meet you in the next lecture. I won't take much of your time, but because I don't want to lose this continuity here. Okay.